Properties of definite integrals. If f is integrable on the closed interval a, b, then the following properties apply. The definite integral at any line x equals c in a, b, is 0. Please refer to the following graph of a function f. The definite integral of f on a, b means computing the net area bounded by f. When the limits of integration are the same, the bounded region is just a line. Therefore, the definite integral, or the net area, is 0. If f is integrable and non-negative on the closed interval a, b, non-negative means f of x is greater than or equal to 0, or f is above or touches the x-axis, then the integral of f of x dx, from a to b, is greater than or equal to 0. That is, the definite integral is non-negative. In the figure, because f is above the x-axis on the closed interval a, b, the definite integral is non-negative, and it corresponds to the area of the shaded region. However, if f is integrable but not non-negative, that is, the graph of f goes below the x-axis on the closed interval a, b, the definite integral refers to the net area of the bounded region, or the difference between the area above and the area below the x-axis, and the definite integral may be less than 0. Reversing the limits of integration leads to the negative of the definite integral. That is, taking definite integral from b to a is the same as taking the negative of the definite integral from a to b. If f and g are integrable on the closed interval a, b, and f of x is greater than or equal to g of x for every x in a, b, then the integral of f of x dx, from a to b, is greater than or equal to the integral of g of x dx, from a to b. In the following figure, consider two functions f and g, where f is above g on the closed interval a, b. The inequality above states that the definite integral of f is greater than or equal to the definite integral of g. And because f and g are both above the x-axis, the inequality also implies that the area bounded by f is greater than or equal to the area bounded by g. In general, the inequality holds whenever f is above g on the closed interval a, b, whether the graphs of f and g go below or above the x-axis, and both are integrable. If the value of f of x is anywhere from m to m for every x on the closed interval a, b, then the integral of f of x dx, from a to b is anywhere from m times b minus a to m times b minus a. Please refer to the graph of a function f in the figure. The inequality means that if f is confined by two numbers m and m on the closed interval a, b, the area bounded by f and the x-axis is lower bounded by the area of the rectangle small m times b minus a, and upper bounded by the rectangle large m times b minus a. Sum or difference rule. If f and g are integrable on the closed interval a, b, then the sum or difference property applies. In other words, an integral operation can be distributed over addition or subtraction operations. Constant multiple rule. If k is a constant, then it can be taken outside of the integral. Additive interval rule. If f is integrable on a closed interval a, b, and on closed subintervals a, c, and c, b, where c is a number between a and b, then the definite integral on a, b is the sum of the definite integrals on the subintervals a, c, and c, b. In the figure, because f is integrable or continuous on a, b, then its definite integral is the sum of two definite integrals in which the common limit of integration c is a number between a and b. Examples. Find the definite integral. Number 1. Given the integral of x squared dx, from 1 to 4, equals 21, the integral of x dx, from 1 to 4, equals 7.5, and the integral of dx, from 1 to 4, equals 3. Compute the following definite integrals. A. The integral of x squared dx, from 4 to 1. B. The integral of x squared dx, from 1 to 1. C. The integral of 2x dx, from 1 to 4. D. The integral of x squared minus 4x plus 3 dx, from 1 to 4. Solution. A. Reverse the limits of integration and take the negative. Substitute the given definite integral. Therefore, the definite integral is equal to -21. B. The limits of integration are equal. Consequently, the definite integral is equal to 0. C. Move the constant outside the integral. Substitute the given definite integral. Hence, the definite integral is equal to 15. Apply the sum or difference rule. Substitute the given definite integrals. Therefore, the definite integral is equal to 0. Number 2. Given the integral of f of x dx, from -2 to 0, equals 6, the integral of f of x dx, from 0 to 2, equals 4, and the integral of g of x dx, from -2 to 2, equals -5. Compute the following definite integrals. A. The integral of f of x dx, from -2 to 2. B. The integral of 7 times f of x dx, from -2 to 2. C. The integral of f of x plus g of x dx, from -2 to 2. D. The integral of 2 times f of x minus 3 times g of x dx, from -2 to 2. Solution. A. Apply the additive interval rule. Substitute the given definite integrals. Therefore, the definite integral is equal to 10. B. Apply the constant multiple rule. Substitute the computed definite integral from -2 to 2. Consequently, the definite integral is equal to 70. C. Apply the sum rule. Substitute the computed and given definite integrals. Hence, the definite integral is equal to 5. D. Apply the constant multiple and difference rules. Substitute the computed and given definite integrals. Therefore, the definite integral is equal to 35. If the integral of the sine of x dx, from 0 to pi over 2, is equal to 1, and the integral of the sine of x dx, from pi over 2 to pi, is equal to 1, compute the integral of the sine of x dx, from 0 to pi. Solution. The function sine of x is integrable, in other words, continuous, on the closed interval 0, pi, and on the subintervals 0, pi over 2, and pi over 2, pi. The definite integral can be computed using the additive interval property. Substitute the given indefinite integrals. Therefore, the integral of the sine of x dx, from 0 to pi, is equal to 2. Write as a single integral. Solution. The given integrals are definite integrals of the same function f. Notice the relationship of the limits of integration of each definite integral. Decompose the first definite integral using the additive interval property. Then, cancel the first and last terms because they have opposite signs and have the same limits of integration. Finally, apply the additive interval property to the second and third terms. Thus, the definite integrals are equivalent to the integral of f of x dx, from 0 to 10. Write as a single integral. Solution. Notice the relationship of the limits of integration of each definite integral. Rewrite the second term using the limit reversal property, so that all the terms have identical limits of integration. Then, combine all the terms using the sum or difference property. Thus, the definite integrals are equivalent to the integral of 5 times f of x minus g of x dx, from -1 to 1. Provide a lower bound and an upper bound of the area of the shaded region. Solution. The definite integral for the area of the shaded region is the integral of the sine of x all over x dx, from -pi to pi. From the graph, f takes values from 0 to 1 on the closed interval, -pi, pi. Use the following property of definite integrals to compute a lower bound and upper bound of the area. With m equals 0, m equals 1, a equal -pi, and b equals pi. The area is bounded as follows. 0 is the lower bound while 2 pi is the upper bound. Symmetric functions. An even function f remains unchanged when x is replaced by -x. That is, f of -x goes back to f of x. If f is an even function, then the integral of f of x dx, from -a to a, is equal to twice the integral of f of x dx, from 0 to a. The following figure illustrates a graph of an even function. It is a function that is symmetric with respect to the y-axis or the line x equals 0. The definite integral of the function from a units to the left of the center of the interval to a units to the right of the center of the interval is just the double of the definite integral from the center of the interval to a. This property is true for any value of a. Keep in mind that the definite integral is the net area of f when f is above and below the x-axis on the given interval. An odd function f becomes negative f when x is replaced by negative x. That is, f of negative x leads to the negative of f of x. If f is an odd function, then the integral of f of x dx, from negative a to a, is equal to 0. The following figure illustrates a graph of an odd function. It is a function that is symmetric with respect to the origin, which means that rotating the right-hand side of the graph by 180 degrees results to the left-hand side of the graph. The definite integral of the function from a units to the left of the center of the interval to a units to the right of the center of the interval is equal to 0. For any value of a, the definite integral is the net area of f, and it is equal to the area above the x-axis minus the area below the axis. Because these areas are equal, their difference is 0. Examples. Find the definite integral. Number 1. If the integral of x squared plus 1 dx, from 0 to 2, is equal to 14/3, find the integral of x squared plus 1 dx, from -2 to 2. Solution. Test whether f is an even or an odd function. Replace x by -x in the given function. F of -x is the same as f of x. Hence, f is an even function. Definite integral may be computed using the property of an even function. Apply the symmetry property for an even function. Substitute the value of the given definite integral. Therefore, the integral of x squared plus 1 dx, from -2 to 2, is equal to 28/3. Number 2. If the integral of the sum of the square of quantity x minus 4 and 1 dx, from 4 to 6, is equal to 14/3, find the integral of the sum of the square of quantity x minus 4 and 1 dx, from 2 to 6. Solution. The graph of x squared is an even function symmetric about x equals 0. The given function can be formed by translating the graph of x squared by 4 units to right and 1 unit above. Consequently, the given function is also an even function about the line x equals 4. Apply the symmetry property for an even function. Substitute the value of the given definite integral. Thus, the integral of the sum of the square of quantity x minus 4 and 1 dx from 2 to 6 is equal to 28/3. Number 3. If the integral of x cubed dx from 0 to 2 is equal to 4, find the integral of x cubed dx from -2 to 2. Solution. Test whether f is an even or an odd function. Substitute -x into the given function. F of -x is equal to the negative of f of x. Hence, f is an odd function. The required integral is the integral of x cubed dx from -2 to 2 is equal to 0. The definite integral is 0 because the net area of the region bounded by x cubed above and below the x-axis is 0. In other words, the area above and below the x-axis are equal. Number 4. If the integral of x cubed dx from 0 to 2 equals 4, tell something about the integral of x cubed dx from -1 to 2. Solution. The required definite integral does not fit directly into a symmetric property. However, we can still take advantage of the odd function symmetric property. We can deduce from the limits of integration that the area below the x-axis is less than the area above the x-axis because from the center 0, -1 is nearer than 2. The net area is the difference between these areas. Therefore, the definite integral is greater than 0 but less than 4. The net area becomes 0 if the limits of integration were from -2 to 2, as shown in the previous number. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.